Hello, ladies and gentlemen, and welcome back to the continuation of our unit on natural disasters, Earth's destructive forces, the world's most feared disasters. This is Mr. Hazen, bringing you this audio documentary and segment number 2, which is entitled Earthquake Terms, Intensity, and Tsunamis. Please follow along with our audio and answer the questions as they come up. You will also be able to see a short little video at the end that kind of wraps up our unit and talk, so make sure that you follow along. We are getting ready to go with segment number 2, Earthquake Terms, Intensity, and Tsunamis. You might have heard of the word seismology, or the word seismic before, I'm sure. But what does it really mean? Well, seismology is the study of vibrations and movement that occurs below the Earth's surface. Seismologists do more than study earthquakes, though. They also look at the forces of what causes tremors and what we as humans can do to prepare ourselves in the event the Earth moves or shakes. Seismologists are asked even by their communities, where earthquakes occur more frequently, to help provide disaster plans. For instance, they can make recommendations on how buildings are designed to help them stay upright during an earthquake, or to prevent them from collapsing. Seismologists are also very good at giving advice. They say when an earthquake strikes, the best place to be is actually outside away from a building or structure. They call this a remote location. Here, you are less likely when the ground shakes and cracks to be near things that can fall on you. If you are stuck in your home and you can't get out, they recommend covering yourself with a blanket and have a hard hat or helmet just in case. Also, they recommend each home have a disaster kit. In your kit, seismologists recommend having the following items: a battery-powered radio, just in case the power goes out, a flashlight, a first aid kit, a whistle to alert emergency personnel if needed, an orange jacket so that you can be seen if you're trapped, and a small food and water supply. Taking these steps is key to survival during these types of disasters. We know that most earthquake activity occurs at the border between two colliding plates. No kidding, right? But many areas of rock that are fractured over time from constant quake activity can form something called faults, which are breaks in the Earth's land masses and actually can be seen on the Earth's surface. Most faults result from tons of energy movement, and we're talking about places in the world that have the most tension and friction. Take, for instance, the most famous fault in the world, the San Andreas Fault in California. It stretches over 800 miles long. Yeah, 800 miles, and is labeled as a transform fault or lateral fault. That's just a fancy way of saying that at this place, the two plates that move basically from side to side. Take a look at the graph on the board. This is a picture of California, and the San Andreas Fault is labeled in red. When an earthquake in California happens, the ocean plate, which is going to represent our blue arrow, will rub and shift against the continental plate, the one in green. How violent and destructive the earthquake is will depend upon the intensity of this shift. The San Andreas Fault has been around for over 5 million years. Not quite as old as dinosaurs, but definitely older than human existence on our planet. But it wasn't actually discovered or identified until 1895. Here's another picture of what the San Andreas Fault looks like from the air. Researchers say that the next big one, a big earthquake that is probably going to happen more sooner than later. How do they know this, you might ask? Well, seismologists say that the zone of stress in the fault has reached a maximum point, leading to more frequent and intense earthquakes. It is not uncommon that a major earthquake could strike California in the next 20 to 30 years, and we're talking devastating, one that can lead to serious global issues. Yeah, I said global. But just how intense does this have to actually be? Well, as you know from our tornado unit, the EF scale measures the intensity of tornadoes after they strike, right? It does not predict when a tornado will occur, but only measures the destruction after a tornado is over. The Richter scale, which has been around since 1930, has been used to measure an earthquake's destruction, but only after an earthquake strikes. This scale has ratings between 0 and 10, with 0 being a very low or very small earthquake, and 10 being a very absolutely destructive earthquake. Take a look at what the Richter scale looks like on the board. Most earthquakes that happen are actually under the intensity of a 1 rating, meaning they actually can't be felt by people on the surface. No earthquake in our history has ever been a recorded 10, but you can imagine what destruction it would leave if we did. Earthquakes that have an intensity of 7 or greater, which are labeled in pink on this graph, can have serious global changes and consequences. What I would like you to do now is you have some questions regarding the Richter scale on your sheet. I'm going to pause for a second so that you can answer those questions, and then we will resume our audio lesson. Thank you so much, ladies and gentlemen, for answering your questions about the Richter scale. We are now going to move on to the last part of our segment number 2. In 2004, a 9.1 earthquake struck the Indian Ocean near the country of Indonesia. Because this earthquake originated in the ocean, the energy released created a huge tsunami, one that killed over 200,000 people on 2 different continents. The tsunami, at its full strength, traveled over 500 miles per hour and completely leveled the landscape of many areas. Take a look at the coast of Indonesia on the board before and after this tsunami hit. So here's a picture of the coast of Indonesia. As you can see, the buildings are upright, everything looks pretty cool, the water's blue, the trees are green. Here's what happened after the tsunami struck this island. Pretty devastating, wasn't it? It was completely leveled. Now the area right there is pretty much barren, can't even grow crops there anymore, so the buildings had to be all rebuilt, but this tsunami completely leveled the area right there. When the tsunami reached the shore, when it hit here, waves were reported to be over 50 feet high, taller than most telephone poles. The earthquake's intensity was so powerful enough to affect the Earth's rotation, decreasing the length of each day by 2.5 microseconds and moving the north and south poles over by 1 inch, which is actually a pretty huge deal. Tsunamis, those huge waves that we just talked about, can only form in large bodies of water, like an ocean or a sea. You won't see tsunamis in lakes or ponds, not even in Lake Michigan. It's just not possible given the amount of energy needed to produce one. Tsunamis, however, are really dangerous. But the good news with tsunamis is that there are actually warning signs that one might strike. First, if you feel an earthquake near the shoreline, it is a great indication that a tsunami will occur because of it. Seek shelter immediately. Higher up shelter, that is. You don't want to be at ground level when one strikes. Find a tall building or hill or mountain and climb up it, quick. Second, if you notice that the shoreline is backing up or moving closer out near the body of the ocean, it's time to get away and find your shelter. A retreating coastline, as they call it, is the best warning sign that a tsunami is coming. You notice some boats sitting on the shore, and that's because the shoreline has moved out quite a bit near the body of the ocean. That's a great warning sign. Get to higher shelter immediately. Just what does this actually look like when a tsunami threatens the coastal areas? We're going to take a short little look at this through our next video. And thank you again so much for listening today and being a good audience.
In 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon, but what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave's speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this disaster? Have attempted to stop tsunamis with seawalls, floodgates, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.